Close your eyes for a moment and imagine a world without fire. No cars traveling on highways, no airplanes crossing the skies, no power stations producing electricity, no factories manufacturing products that support our daily life. Modern civilization, as we know, it would simply stop. Hidden behind almost every technological advancement in one remarkable process, combustion. Combustion is much more than a flame. It is a conversion of chemical energy stored inside fuel into useful forms of energy that power transportation, industries, and electricity generation. But as engineers, we don't simply observe fire. We ask deeper questions. What exactly happens during combustion? How do molecules release such enormous amounts of energy? Why can't all of this energy be converted into useful work? And are there better ways to harness chemical energy in the future? This question leads us into one of the most fascinating topics in thermodynamics, reacting mixtures and combustion. Throughout this presentation, we will explore how engineers analyze reacting systems using the fundamental principles of thermodynamics. We will investigate mass conservation, energy conservation, entropy generation, adiabatic flame temperatures, and finally, discover the technologies that can even bypass the conventional combustion entirely. So today, I invite all of you to begin this journey with me. Welcome to the Chapter 13, Thermodynamic Analysis of Reacting Systems. Our mission begins now. Before learning how combustion works, we should first ask a simple question. Why do we even study combustion? The answer is everywhere around us. First, consider a car engine. Inside its cylinder, fuel and air react rapidly, releasing the chemical energy that push the pistons and produce the mechanical work. Next, think about an aircraft engine. Combustion produces extremely hot, high-velocity gases that generate thrust powerful enough to lift the hundreds of passengers into the sky. Then we have power plants. Large amounts of fuel are burned to generate steam or hot gases that drive turbines and produce electricity for entire cities. And finally, industrial boilers rely on combustion to provide heat required in manufacturing processes and chemical industry. These examples demonstrate that combustion is one of the most important energy conversion process ever developed by humanity. In fact, combustion converts the chemical energy into useful energy forms and power, transportation, electricity generation, and industrial applications. More importantly, over 80% of global energy conversion systems still depend on combustion process. Therefore, understanding combustion allows the engineer to improve efficiency, reduce fuel consumption, minimize the emissions, and design more sustainable energy system. Now that we understand its importance, let's examine our mission objective. By the end of this chapter, we should be able to first, explain the combustion reaction and reacting mixtures. Second, we can determine the theoretical air requirement and excess air requirements. Third, apply the mass conservation principles to combustion system. And fourth, apply energy balance using the enthalpy of formation. Fifth, define the adiabatic flame temperature. Sixth, explain the entropy generation and irreversibility during combustion. And finally, understand the basic principles of the fuel cells. In other words, we are about to master the complete thermodynamic framework required to analyze the reacting system. The human quest to extract chemical energy. Now our journey truly begins. Humanity has always searched for ways to extract the useful energy from fuel. At the molecular level, combustion is essentially a rearrangement of atoms. Existing chemical bonds break apart, new bonds are formed. During this process, energy is released. This is why combustion can power engines and produce the electricity. However, thermodynamics immediately teach us an important lesson. Energy extraction is limited. We cannot convert all chemical energy into useful work. There are always losses and restrictions imposed by the physical laws. Another important idea is that the maximum possible temperature during combustion occurs at the adiabatic flame temperature. This represents the highest theoretical temperature achievable when no heat escapes to the surroundings. Furthermore, combustion processes are irreversible. Irreversibilities generate entropy. reducing the amount of energy that can be converted into useful work. Now, to analyze combustion systematically, engineers imagine a standard reacting control volume. On the left side, fuel and oxidizer enter the system. These reactors may consist of fuel mixed with oxygen or air. Excuse me. Mass enters the control volume. Inside the control volume, chemical reaction occurs. Chemical energy begins transforming into thermal energy. Heat transfer may occur through the boundaries. Work transfer may also occur. On the right side, products leave the control volume. These products usually have higher temperatures than the incoming reactants. Therefore, this control volume model provides a universal framework that engineers use to analyze every reactor system from engine to power plants and industrial furnace. Our first thermodynamic power-up is mass conservation and stoichiometry. The law of mass conservation states that matter can neither be created nor destroyed. Therefore, during combustion, the total mass of reactants must always equal the total mass of products. To illustrate this principle, consider methane combustion. Methane is represented by CS4 is our fuel. The combustion reaction is CS4 plus 2 times O2 plus 3.79 of nitrogen produce the CO2 plus 2 H2O plus 7.52 nitrogen gas. Let us understand each component. One molecule of methane contains one carbon atom and 4 hydrogen atoms. To completely oxidize these atoms, 2 molecules of oxygen are required. The products become 1 molecule of carbon dioxide and 2 molecules of water. But where does the 7.52 nitrogen come from? This comes from air composition. Atmospheric air consists approximately of 21% oxygen and 79% nitrogen. This means every mole of oxygen entering the system is accompanied by 3.76 moles of nitrogen. Nitrogen is considered chemically inert in this simplified combustion model. However, it absorbs heat and significantly affects the fine temperature of the combustion products. This is why combustion calculation must always account for nitrogen. Now let us define another extremely important engineering parameter, the air-fuel ratio, AF. On a mass basis, the air-fuel ratio is equal to the mass of air divided by the mass of fuel. On a molar basis, the air-fuel ratio is equal to the number of moles of air divided by the number of moles of fuel. These quantities are usually calculated using the molecular weights. For example, the molecular weight of air is approximately 28.97 kilograms per kilomole. The air-fuel ratio serves as a master diagnostic tool because it tells the engineers whether enough oxygen is available to achieve complete combustion. Now, we can diagnose the condition of our combustion process. There are 3 possible scenarios. The first scenario is called theoretical air or stoichiometric combustion. Here the equivalent ratio phi equals 1. This means exactly the minimum amount of air required to completely oxidize all carbon, hydrogen, and sulfur present in the fuel. Since all oxygen is consumed during combustion, no free oxygen remains in the products. The product usually consists of carbon dioxide, water, sulfur dioxide, and nitrogen. The second scenario is called excess air or lean combustion. In this case, the equivalent ratio is less than 1. More air than necessary is applied. For example, 150% theoretical air means 50% more air than required is entering the combustion chamber. As a result, some oxygen remains unreacted in the products. The amount of nitrogen also increases because additional air brings the additional nitrogen into the system. And the third scenario is deficient air or rich combustion. Here, the equivalent ratio is greater than 1. There is insufficient oxygen to completely burn all fuel molecules. Consequently, incomplete combustion occurs. Unburned fuel may remain, carbon monoxide can be formed, other undesirable species may also appear. Rich combustion generally reduce efficiency and increase the pollutant emission. Therefore, one of the most important responsibilities of engineers is controlling the air-fuel ratio so that combustion occurs under the desired operating conditions. Now, let's apply everything we have learned. Consider the complete combustion of methane. The balanced chemical equation is CS4 plus 2 times O2 plus 3.76 N2 produce the CO2 plus 2H2O plus 7.52 N2. The question is, how much theoretical air is required to completely burn 1 kilomole of methane? To answer this, we examine the balanced equation. First, 1 kilomole of methane requires 2 kilomoles of oxygen. This requirement comes directly from the stoichiometric coefficients. Second, since each kilomole of oxygen brings 3.76 kilomoles of nitrogen, the amount of nitrogen entering the system becomes 2 multiplied by 3.76. This gives 7.52 kilomoles of nitrogen. Therefore, total theoretical air consists of 2 kilomoles of oxygen plus 7.52 kilomoles of nitrogen. Consequently, theoretical air equals 9.52 kilomoles of air. This example may appear simple, but it demonstrates one of the most fundamental calculations in combustion engineering. Every combustion system, from automobile engines to gas turbines and industrial furnace, begins with determining the correct theoretical air requirement. Without proper air supply, combustion becomes inefficient, temperature change, pollution increase, and system performance deteriorates. And with that, we have successfully unlocked our first thermodynamic power, mass conservation, and stoichiometry. But our journey is far from over. We now know how fuel and air combine. Yet, an even bigger question remains. How much energy can actually be extracted from this reaction? To answer that, we must unlock our next power, energy itself. To be continued in part 2, the energy ascension arc. Thank you.